All right, so today we're starting Objective 3.2, and the topic for today is beyond just the algebra of functions. Now, last year in math analysis, you should have learned how to add and subtract and multiply two functions. If I give you two functions, add them, subtract them, multiply them, divide them. You might also remember that you really had to pay attention to the domains of those two functions, because you can't add two functions if they don't share the same x's, or you can't subtract or do any of the operations. So it's really important to pay attention to that. What are our essential questions today? How are we going beyond just doing some algebra, right? Just combining some like terms or multiplying or dividing our variables and our constants. Here's our essential question. How do I find the sum, difference, product, and quotient of two functions algebraically? So we'll review that. But today we're going to dive deeper. How do I add them like analytically on a table of values? And how do I add them graphically? So the other thing to pay attention to pay attention to as we're going through the lesson is, why do you even have to pay attention to the domain of both functions, whether you're adding, subtracting, multiplying, and divide them. So let's start off with the definition for the sums, products, differences, and quotients of functions. So just so you know, we can add, subtract, multiply, and divide two functions to obtain new functions. Okay. However, what you have to do is also pay attention to the fact that we can only perform those operations, add, subtract, multiply, divide, over the shared domain of the two functions. So if one function has a domain of negative infinity to positive infinity, and the other one has a domain from -1 to infinity, well, you can only add, subtract, multiply, and divide them over their shared domain. So you could only add, subtract, multiply, and divide that specific case from -1 to infinity. So that is critical, right? Because if I were to take this graph here, I'm just going to draw a real quick picture, okay? And let's say I have this graph and it looks something like this. So it looks like this. So it's this funky little function here. And then I'm going to do, so that's going to be function f. And then I get another function that looks something like this. Okay? And I ask, and that'll be function g. And I ask you to add those two functions. Well, I can only add them where they share the same domain. And so that would happen, let's see, right here is where they start to overlap, and then they stop overlapping right here. So I could actually only add those two functions, or subtract them, or multiply them, or divide them over their shared domain where they have x's in common. And so that's what's really critical. So hopefully that little picture there helps you to understand what I was referring to when I said we can only perform these operations over the shared domain of the two functions with an S. There we go. All right, so just a couple of reminders for the algebra of functions here. If I have the f plus g of x, what that really means is the f of x plus the g of x. Okay, that's what that means. All right, where their domains overlap, where they share domains. So that'll be true where their domains overlap. the domain of the first function and the second. This one here is the subtraction. F minus g of x is the same as f of x minus g of x. And then you have the common thing there where their domains overlap. And then the f of times g of x means the f of x times the g of x. Okay, and where their domains overlap. Now these three situations will all have the same domain. Okay, so once I give you two functions and I say find the domain of their sum, the domain of their difference will be the same and the domain of their product will also be the same. Now the only one that's a little different is when you're dividing, because you're putting a function in the denominator. So the f divided by g of, by the way, that should have an x on it there. I'll fix that. Looks like this. This is the f of x over the g of x. Okay, but remember that the g of x cannot equal 0 because that is in the denominator. So that is a restriction on the domain. So it's going to have an additional restriction along with where their domains overlap. So just clue into that when you are doing division, when you're finding the quotient. Whatever function you put in the denominator, you have to find the zeros of that function so that you can eliminate those from the domain because they're restrictions. Okay, so let's take a look here at example 1. It says given that the function of x is x plus 1, and I think I'll look at that in blue here. And the g of x, switch to red, is the square root of x plus 3. Find each of the following. So let's look at the domain of f and g. So here we have f of x equals x plus 1. All right, so it's a linear function. And x can be anything I want. It doesn't have any restrictions. So its domain would be from negative infinity to infinity. For our g of x function, that's the square root of x plus 3. Well, remember that underneath the square root has to be non-negative, so we'll say x plus 3 must be greater than or equal to 0. So that means x has to be greater than or equal to negative 3. Therefore, the domain of the second function is from negative 3 closed to infinity. So remember what I said. Now if I want to add, subtract, multiply, or divide them, I can only do that where those two graphs overlap. So let's take a look at the domain of f plus g of x. So here's the domain of f of x. It's the entire number line, right? And then here's the domain of, I'm going to put a negative 3 right here, the domain of your g of x, and it goes like that. And so the domain of f of x plus g of x is that space here where the two domains overlap. And so its domain, and I'm going to do the addition of it in green, would have a domain, and I shouldn't put an equal sign there, will have a domain from negative 3 to infinity and inclusive of negative 3. And I'm going to show you what that looks like on a graph here in just a second. Okay, so now let's add these two functions algebraically. So the f plus g of x really means the f of x plus the g of x. So I'm just going to remove the f of x and the g of x and substitute in the other side of those equations or their values. So this would look like this. The f of x is x plus 1, so we're going to substitute that in, and the g of x is the square root of x plus 3. All right, so let's simplify that if we can. We'll distribute here. Well, there's nothing really going on there, so that's just x plus 1 plus the square root of x plus 3. And to be honest, there really isn't anything else that we can do with that. And so that is algebraically the solution to that. Okay? All right, But let's remember that our domain is between -3 and infinity. So we can't plug in, for example, -10, because -10 wouldn't be in our domain. So x could never equal -10. Let's go ahead and do, this should say problem D, and this should say problem E. I'll try to fix that before I go to bed here. Okay, so let's take a look at this next one. Let's find the f plus g of 6. Okay, so first of all, we've already added the f plus g of x. And so we already know that the f plus g of x is equal to x plus 1 plus the square root of x plus 3. So if we want to find the f plus g of 6, well, we would just replace the x with 6. So that would be 6 plus 1 plus the square root of 6 plus 3. And then, of course, we would simplify that to 7 plus the square root of 9, which is 7 plus 3. So our final solution would be 10. So the f plus g of 6 is 10. All right, so that worked out pretty good. And that was okay because 6 is in our domain. Remember that our domain is between -3 and infinity. Those are the values that we can actually plug in to the sum of these two functions. So let's look at E here. E says find the f plus g of -4. But here's the thing. Our graph is from -3 to infinity, and -4 is over here. It is outside of our domain. Therefore, the solution does not exist because I cannot actually plug in a -4. But let me show you algebraically why this is the case, because you may not be paying attention to what is the domain of this, the addition of these two functions. So if we were to do the f plus g of -4, so remember that the f plus g of x is equal to x plus 1 plus the square root of x plus 3. And we're going to perform the f plus g of -4. So we would plug in a -4 for x. So that'd be -4 plus 1 plus the square root of -4 plus 3. And if we were to continue to work that out, I'm going to circle that there and get it out of the, separate it. Here we go. That's -3 plus the square root of -1. Here's the problem. This is not real. Therefore, we don't have a solution to this equation. So this situation does not exist because -4 is outside of the domain of our new function. Okay, so that's why it's important to find the domain of the two original functions and then figure out where they overlap so you know which values you can plug in and which values you shouldn't. Okay, so now let's go back and let's look at this analytically. How would we add the f plus g of x analytically? So I'm just going to pick some values here. I think I'm going to pick -3, -2, 1. Hang on, I just have to remember what I'm doing here. And 6. So these are the points that I'm going to pick. And I did pick them specifically for a reason. All right. And now I'm going to go in and put in my f of x. So remember that the f of x is x plus 1. So I'm just plugging in this x. So -3 plus 1 is -2. Okay. Now we'll plug in a -2 plus 1 is -1. -1 plus 1 is 0. And 6 plus 1. Wait, that's not -1 plus 1. That's 1 plus 1 is 2. Let me fix that. That is really bad. So 1 plus 1 is 2 and 6 plus 1 is 7. All right. So there's that graph. So let's go ahead and graph that line on here because we're also going to add these two functions on the graph. So we have -3, -2, -2, -1, 1, 2, and then 6, 7, and you can see that's that linear equation right there. And of course, we could have added, we could have just graphed that because it was in slope-intercept form. Our y-intercept was 1, and we had a slope of rise 1, run 1, so you could have graphed that really quickly like that. Let's go back now, and let's do the g of x. So our g of x is equal to the square root of x plus 3, and we're going to be plugging in these x's. And the reason that I chose these specific x's is because they're going to make nice, beautiful, perfect square roots. So we're going to plug in here a negative 3. Square root of negative 3 plus 3 is the square root of 0, and that is 0. So I'm going to go ahead and graph that. Negative 3, 0. All right, so this is where their domain begins to overlap. Let's plug in a negative 2 back to the graph, back to the function here. So let's analyze that. The square root of negative 2 plus 3 is the square root of 1, which is 1. So negative 2 up 1 is that point there. Right, let's plug in a 1. So square root of 1 plus 3 is 4, and the square root of 4 is 2. So we're going to graph the point 1, 2. So these two graphs are going to intersect at that point. Then let's plug in a 6. Okay, this last one. The square root of 6 plus 3 is the square root of 9, and the square root of 9 is 3. So 6, 3 is this graph here. So 6, 3. So this is your square root function here, and it is curving up nice and gently like that. So there are our two functions. So and you can see where they overlap. Hopefully you can see that they start overlapping right here where x equals 3, and then they go, both of them go off to x is infinity, and so there's our domain. So this is just a different representation of the domain of the two when we add them. Because I can't add this function here, I can't add where x equals negative 4 if on my red function or my g function f does not equal, I can't plug in a negative 4, so I can only add these two where their function outputs belong. So let's do the f plus g of x. So what does that mean? And I'm going to do this in green. What you're just going to do is you're going to add your f of x. Remember, that's just your f of x plus your g of x. That's what that means. All right, so we're going to do negative 2 plus 0, that's negative 2. So our f plus g of x is going to be the point at the point negative 3, negative 2. All right, so I'm going to graph that. Negative 3, negative 2 is right there. All right, then we're going to do the f plus g of x, or the f of x plus the g of x here. So negative 1 plus 1, that is 0. So this is going to be the point at x is negative 2, and f of their sum of their outputs is 0. So that would be negative 2, 0. So that's that point right there. We'll add these two, that's 4. So that would be the point 1, 4. So that's here. And then the last one here is 7 plus 3 is 10. So the resulting point would be at 6, input 6, output of 10. And you recall that we actually did find that when we were adding that algebraically. We actually did find that. So 6, 10 would be right here. So what I have to do with those points is, this is a pretty funky equation. It's a square root function, okay, because it's got that square root in it. So it's just a curve, but because it's got a line in the equation, the x plus 1, it kind of turns the curve on its side. So the graph looks something like that. So I'm going to highlight that. I'll grab my green highlighter here to indicate that this graph right here is actually the sum of those two graphs. So that's the f plus g. Actually, I don't need to do anything. That's just the f plus g function there. Now, I actually could have added these functions together just on the graph. So let's see if you can figure this out. Watch me do this. So I'm going to add the blue function plus the red function, and I'm adding their function values. So let's start right here. This is x equals 7, and this is y equals 3. Y equals 7 and y equals 3, and 7 plus 3 is 10. So at x equals 6, you have 7 plus 3 is 10. And then the next place where they both intersect at a nice intersection is right here, where your blue output is 2 and your red output is 2, and 2 plus 2 is 4. So there you have that. The next place they both have a nice intersection is right here, this blue point and this red point right here that I just changed. So that's -1 plus 1, and that is 0. So you can see that I just added those 2 points. And then the last 2 points where they share a point are on the x-axis on the domain. Nice intersections, excuse me. They both have nice intersections is right here where x equals -3. And so that would be -2 plus 0, which is -2. And there you have. So you could actually just add them if you add their function values on the actual graph. So that's taking it beyond the algebra, looking at it analytically, and then looking at it graphically. Now I just want to show you that this is actually true in Desmos. So this green line that I've just drawn, this green curve, I want you to see it on Desmos because it's something else that you're going to have to do. And so I'm going to come in here to Desmos and take these functions out that I have in here. All right, so we're going to add in this first function. We're going to actually type in the f of x equals, and then what was it, x plus 1. So there's our first function. And then our g of x, so we're going to type in g of x equals the square root of x plus 3. And there are the two functions that we drew. Now what's nice is, now that I've defined where the f of x is and the g of x is, I can tell Desmos to take the f of x and add it to, or add the g of x. And maybe if I do a good job typing here, you can see it. And so look at that. Remember my green line that we drew? I'm going to turn those other two off. Look at that. That is actually the graph that we drew with all those points. There's 610 right there somewhere. There it was. Anyway, there it is. That's the resulting. So if I wanted to subtract the two functions, here's what would happen. Guess what? So now I'm multiplying. Okay, so I took the addition. So that's what it looks if I multiply them. Here's what it looks like if I subtract them. And then I wonder what it would look like if I divided them. So I'm going to divide them. So watch that. So that's something that's really interesting. And then you should use this tool when you're doing your assignment. And so there's your f of x divided by your g of x. So Desmos is pretty nice. Makes it pretty easy to check your work and look at the resulting function. All right. Let's go on to the back side. So here on the back side, what I did was, we're just going to do this algebraically, and then I did make a video. I did make a video of the analytics and the graphs of these four functions. So if you wanted to look at how I was adding, subtracting, and multiplying them and dividing them, you should take a look at that video, because I would challenge you to actually think about what we're doing here when we're going beyond just the algebra. So let's look at these two functions, or these two functions here. So we have our f of x is this quadratic, x squared minus 4, and our g of x is this linear equation, x plus 2. So we're going to find each of the following. So first let's find the domain of f and g. So if we have f of x equals x squared minus 4, well, that's a parabola, and parabolas don't have restrictions on your domain. So your domain is absolutely unrestricted. All right. Your g of x is linear, x plus 2. It also could have any x I want, so my domain would be -infinity to infinity. So let's just think about what the domain of adding, subtracting, and multiplying them is. Because remember what I said back up here. You can add, subtract, or multiply them where their domains overlap. So they would all have the same domain when you add, subtract, and multiply them. And since they overlap everywhere, the domains of these two functions when we add, subtract, and multiply them would be unrestricted. But remember that when we divide them, our denominator can't equal 0, so it will add one restriction. So our domain of f plus g, f minus g, and f times g, because we have the domain is negative infinity to infinity on your f, and the domain of your g function is also negative infinity to infinity, then the domain of, I'm just going to do this in green, f plus g, f minus g, and f times g would all have a domain of negative infinity to infinity. Okay, no restriction. But if we were to do the f divided by g, that means that we're doing this. We're taking the f of, let me make my fraction bar here. What we're doing is taking the f of x, which is x squared minus 4, over the g of x, which is x plus 2, and we are remembering that x plus 2 cannot equal 0, and so x cannot equal negative 2. And so that means that that would punch a hole in our domain, which was originally, let me do it in green here, sorry about that, we're doing this in green. So our domain of f divided by g, that's this one, goes from negative infinity to infinity, but it has a hole in it at negative 2. So our domain here would be from negative infinity to negative 2, open, and then negative 2 to infinity. So we have that one additional restriction to clue into. Okay, and so there we have that. So when we're looking at problem C, D, and D, again, I did that. I can't believe I did that. All right, so this is going to be E and F, and there, that's still G. Okay, so let's look at that. Let's add these two functions and see what the resulting function is. So remember that this really means the f of x plus the g of x. All right, so we're taking essentially here this quadratic function, which is x squared minus 4, and we are adding our g of x. And anytime I replace one term with another set of terms, I always use parentheses. It's really critical when you're subtracting or multiplying, so I just always do it. And here we're going to add these two here. So that would be x squared minus 4 plus x plus 2, and then we'll combine like terms, and our resulting f plus g of x function, we're adding a parabola plus a line, and guess what we're getting? X squared plus x minus 2. This is a parabola. So the resulting function, the new function, would also be a parabola with a domain that is unrestricted. And so there would be our solution. For our f minus g of x, remember we're doing the f of x minus the g of x. Okay, and so I'm going to put my minus sign in there. I'm going to put some parentheses because I'm going to replace the f of x with x squared minus 4, and I'm going to replace the g of x with x plus 2. And here's where that set of parentheses right here was really critical. I have to distribute that minus sign, or that negative 1, to both of those terms. So we get x squared minus 4 minus x minus 2. Combining like terms here, here's our f minus g of x. Our new function is x squared minus x minus 6. Another parabola. So I guess we can come to some kind of conclusion that if we're adding a parabola plus a line, we get a new parabola. Or if we subtract a parabola and a line, we get a new parabola. Okay, let's do the f times g of x. So remember that really means the f of x times the g of x. So we're going to just get out our parentheses here and replace f of x with x squared minus 4. And our g of x is x plus 2. And so we'll go ahead now and multiply those two together. So we'll distribute. So that'll be x cubed plus 2x squared minus 4x minus 8. And so our resulting solution, actually we can't combine like terms, so I think what I'll do is just move this up here. We can't combine like terms. So what is our result here? What are we graphing here? Okay, that is a cubic function. So it probably looks something like that. This is a cubic function. All right, so if I multiply a quadratic times a linear, just think about it. If I'm doing x squared times x, that's x cubed. That's a cubic function. Okay, so the resulting function is a cubic. Let's look at this last one here. All right, so we're doing the f of x divided by the g of x. And this one is going to require a little extra work because this is a fraction, and you always have to make sure that your fraction is in simplest form. So let's go ahead and fill this out. So I think I'm going to go horizontally with this work here. And I'm not going to use equal signs. I'm going to use arrows just to indicate my movement forward. So my f of x is x squared minus 4. And my g of x is x plus 2. Remembering that x is not allowed to equal negative 2 because of our domain restriction. So remember, that is our one domain restriction. Now we have to simplify this function. So we need to make sure that there's not a common factor. So in our numerator, that's a difference of squares. So I'm going to factor that to x minus 2, x plus 2, because that's the difference of squares. You should recognize that. All over x plus 2. All right. Now what we do is we go, all right, so common factor, common linear factor of x plus 2. I can cancel that out. So my final answer here would be x minus 2. So the f divided by g of x is linear for x equal minus 2, as long as x does not equal negative 2. Because we do have that restriction. And so that's interesting. When we divided a quadratic by a linear, we got a linear. So let's think about that for a second. If I take something that's x squared and I divide it by x, well, guess what that equals? That equals x, right? Because so when you divide a quadratic by a linear, you get a linear function. All right, so there is your solution. Last one that I'm asking you to do here is the g times g of x. All right, so g times g of x. So that's the g of x times the g of x. So we're just going to plug that in. So that would be x plus 2 times itself. So we're doing a linear equation times a linear equation, and that gives us, let me get my, this would be x squared plus 2x, come back, plus 2x plus 4. So the g times g of x, x squared plus 4x plus 4. So it is quadratic. All right, and so, and since there was no restriction in x plus 2, domain restriction, then there's no restriction in that function either. All right, so there you have the algebra of functions with also some graphic examples and some analytic examples. And then what I put here is just an option for you if you wanted to try to do one of these four. I did make a video of how to analyze those four. Actually, these four, excuse me, C, D, E, and F. So if you wanted to watch that video, you could. But maybe you could give it a go. Maybe you could just do problem C, and you could pick, I'll give you some good points to pick. Let's see. Let's pick -3, -2, -1, 0, 1, and 2. Just pick maybe those points and see how that goes. Find your f of x outputs for those domain values and your g of x, and then add them or subtract them. I would say that it would probably be pretty difficult to multiply them because it'll be a cubic function, and those are a little bit hard to imagine when you're graphing just random points. The division would be pretty easy because that's just linear. So you could look at that analytically and graphically if you wanted to. One other thing I would like to mention is if I were to give you this function, the f of x equals 1 over x plus 2, and the g of x equals x over x plus 1, and I wanted you to find the f of x plus the g of x, well, you're going to have to find common denominators. So I'm just going to remind you how to do that real quickly. So that would be 1 over x plus 2. And remember, that means x cannot equal negative 2. Okay? Plus x over x plus 1. And so that one has a domain restriction of negative 1. So there's our two domain restrictions. X can be anything else I want, so think about that. And then in order to add fractions, we have to have common denominators. So it's just like me going 1 over 2 plus 2 over 3 or something like that. In order to have common denominators, you would have to multiply this denominator times 3, top and bottom, and this one times 2, top and bottom, so that you could say, okay, so the denominator is 6, and then the numerator would be 3 plus 4, and that would be 7/6. So same idea, if I'm working on this problem here, I would have to have common denominators here. So I would multiply this times x plus 1 on the top and the bottom. And then this side over here, the second function, I'd have to multiply times x plus 2 over x plus 2. And so the resulting would be this, x plus 1 plus x squared plus 2x all over x plus 2, x plus 1, and then simplify the top here. That would be x squared plus 3x plus 1 over x plus 2, x plus 1. Okay, and so you might see a problem where you have to do something like that. And so just remember, when you're adding and subtracting fractions, that your denominators have to be the same. And so that's it. That's all I have for you for now. You'll have an assignment to work on Canvas. Have a good day.